In this episode of FUM0106 machining, we are not making a tool. What we are going to do, we are having a short discussion about thermal expansion of metals. And then we make a device which takes advantage of this thermal expansion, and you probably can guess it, we are making a thermometer. Well, it's not an exact device, it's just demonstrating the expansion and contraction of metals, how they behave with temperature. So, well, first a little bit of theory and then a lot of quite cumbersome machining, and let's see what then happens. So, let's go on with the theory. Well, so every material, solid material, everything has a tendency to become longer, thicker, has more volume when it warms up, and when it cools down it shrinks back to some size. And for metals this is, we are sometimes facing issues while measuring diameters, for example. If the object to be measured is too hot, it will give you too large diameter, resulting in overshooting your machine. So, but how much do these metals become larger? How much do they shrink? Well, actually there is, when I did a search in internet, and the unit for measuring, and sorry guys, I'm doing this in metric, this is a metric system. There is also an imperial system with Fahrenheit and inches and so on, but this time it will be Celsius and millimeters. It will be coefficient. It's not dealing with, the only metric part is this Celsius here. So, what this means that for every degree of Celsius, a change in Celsius, there will be a change in dimension. And the unit in this case is ppm, parts per million. This is what it is 10 exponent minus 6 is all about. It's parts per million. So, there is a list of different temperature coefficients in the internet. You can search with Google, for example, and aluminium, for example, has temperature coefficient of 23 ppm. And steel, on the other hand, is a little bit smaller. Well, this depends on alloys, and so does it depend on steels, but these are, well, it's in the same planet at least, the figures for different steel alloys. So it's about 12 ppm, parts per million. Okay, so assuming we have a piece of material, aluminium, for example, and it's 100 millimeters long. If now the temperature rises 1 degree Celsius, what does this mean? We calculate this one. So it will be 23 times 1 per million. That's easier for me. 1 per million no, yeah, how many? 5 zeros there. Times 23. And now, since this is for every millimeter, so we multiply this even more, we multiply this with 100. So, for every degree of Celsius, it seems like this becomes, if the temperature rises, it will become here 0.0023 millimeters longer. Well, it's actually 2/1000 of a millimeter, I believe. Let me calculate this one more time. 1 per 4 million equals to that. 23 times 100. Yeah, it's 2/1000 of a millimeter longer. Okay, so and this is for every degree Celsius. If we now have 10 degrees, it will be 2/100 of a millimeter longer already. Okay, and so on. So basically you could measure temperature just by measuring the length of a known, in a known temperature of a known object which is of known material, etc. And then of course you have to compensate for your micrometer, which is also made of material, which also is, will become larger and or smaller depending on the temperature. Okay, so in this case, if we want to measure temperature with this one, so we could make a thing that is something like a long thing, like that, and then we would have something like a flexure here, and then some bearing here. So when it becomes longer, these will go up and down, depending whether the temperature changes. Okay, but now we have a problem. Where do we put, because we need to bind this point here with that point here. Okay, let's say this is aluminium. So it means that if we put this some plate behind here, which is also aluminium, what happens is that the plate also becomes larger with the temperature, and there will be no change in here. It compensates itself. But if we make this out of steel, so there is an aluminium thing and then a steel backplate. So then we are going to have a difference here, but it's not 23, and therefore I fetch this steel, so it's actually 23 minus 12 ppm. Because now this steel doesn't grow so fast as the aluminium, so there will be something like, let's approximate, it's 10 ppm. So what we are going to end up for every degree, if this is 100 millimeters long, for every degree there will be a change of 1/1000 of a millimeter here, relative to the base. Okay. Well, that could be usable actually. Let's make this one. Let's see how it goes. Well, we are going to simplify this a little bit. It becomes too complicated if I make it like I designed here, there in the paper. Well, what we are going to do here is, this is about 30 centimeters, this is just some hot rolled steel. This will become one part of that. And then this is aluminium, we take equal length of this one. Okay, then we have the measuring system. This is some steel, mystery steel, and it will become here in the bottom. Binding these two things here down together. And after that, on the top, I will use, this is tool steel, and it will be sitting on top here, like that. And this will be the steady part with this, steel bar. And then there will be a flexure. I mean, it will be cut off, and then I will slit a very thin slit with slitting saw there on both pieces, and then I will use this. This was this is a dull. You know what this is? This is just a hacksaw blade, and this one is really good flexure. Actually, it should do the trick. So. What I'm and then because this aluminium is really soft, actually, what we need to do is to at this end where there is this flexure thing here, it needs to be hard. So therefore I will actually put carbide insert. I have a selection of all sorts of miscellaneous carbide inserts. I will put one here. So after that it should be hard enough so that it won't go there. And what I'm using as a bearing here between these two materials, it's a ball bearing actually. I will make a dent into this one, and then we will have a ball bearing there, and it should hold itself on place. And then when we have a flexure here, so I think we will meet in the lathe. The machining is now over. It was quite simple things to do, especially because this milling machine has abilities to do angles quite easily. Okay. Anyway, now what I have done here is a setup. So we have, this is the device we have made, and there is one carbide insert and a ball bearing ball, and then we have this pivoting system here. Okay. We are going to see whether this works or not. So here is the steel bar and the aluminium bar. So if we heat them both, this should still go up. If we heat only the aluminium, that should actually go faster up. If we heat only the iron, it should go down, even if it is heating up. Okay. So, it's not very easy to heat them that way. So I will just put some heat onto there. I don't want to touch it by fingers too, because it's very sensitive. It's really sensitive. And then we have this scale here. I will put this region in your picture so you can see what happens when I heat it up. Well, yeah. So let's start heating and see whether this is sensitive enough to be used as a thermometer, or whether this is just scientific experiment. Anyway, it has been fun. But let's see how it works. Okay, let's start. I have here a heat gun, and I'm now starting to warm it up. Sorry about the noise. Let's see what happens here. Okay, now let's cool it down somehow. I have the brake cleaner. That should work all right. On these surfaces, let's see. Yeah. Okay. But the is not enough to be heavier. Let's see how hot it is. Well, it's like still quite hot. Something like 50 degrees at least. Going down more. Oh yeah. Now it's just a little bit above room temperature. Oh yeah. And now if I heat it up again. Okay, it works, but this is really not sensitive enough to be a visible thermometer. Okay, whether this thing can be used as a real-life thermometer? No. It's just not sensitive enough. You should be able to see deviations of 1 degree at least, and it's quite bulky, it's big and heavy and whatever. Okay, but what this is, it was a proof of concept. It means that you really can actually build a thermometer based on expansion of two different metals, but the execution should be way better what I made here. The accuracy of the components, maybe you could, for example, put a dial indicator here. That would be one concept of doing this. Well, sacrifice one dial indicator just to measure temperatures. Okay. Another concept would be, well, another thing about this was that it was fun to make. Yeah. Anyway, waste of material? No. Actually, these can be used. I intentionally made them very long so that I don't waste the material. I don't like that. The material that got wasted is these pieces of tool steel. 3 pieces of that, and well, I have a lot of this stuff on myself, so I will show a picture for you. So this is something. Actually, I learned something about this material. It's very easy to machine once you know how to, and I know from experience that this is easy to harden. So just warm it up to cherry red until the magnet doesn't touch it, and then you drop it into oil. After that it becomes really glass hard. You have to relieve it somehow. Anyway, that's it. So hopefully you like this little experiment. And well, the next time in FUM brick machining I will figure out something else which is well, not a tool, but maybe something useful though. So, till then, see you!